I'm Brian Evans. I'm a professor in the Earth Atmospheric and Planetary Sciences Department. We do rock deformation and rock physics. The laboratory that we have here is designed to produce data, experimental data on physical properties of rocks under high pressure and temperature conditions. The field is important because it's a component of understanding the Earth. And without the constraints that the laboratory data put on the understanding of rock properties, we're at a loss to explain the seismic signatures that we get, or just looking at an outcrop. Understanding how the data are obtained is important. Knowing the limits of the data, the accuracy and the precision is also important. How well do you know things, and how poorly do you know things? And those are all important in understanding the processes and trying to form an integrated picture of what's going on deep in the Earth. The constraints that the rock physics data have given, both in practical applications and in scientific applications, has been huge. So understanding the importance of fractures on the properties of rocks and the transmission of fluids is something that has been was started in this lab, actually, and has been just an incredibly important component in understanding fluid flow in the Earth. The same is true of the creep properties. So being able to know how processes can occur in plate tectonics or mountain building, the limits that are placed on the processes from the data from laboratories like this has really been invaluable in understanding deep Earth deformation. The lab came about by Bill Brace, who received a PhD in field structural geology in the early 50s. And then he was hired here after a period of studying in Austria with Bruno Sanders, and at Harvard with Percy Bridgman. He was hired here as an assistant professor. And I actually brought a statement that he wrote in his PhD thesis, which was studying the structural geology of the Green Mountains in Vermont. And his last paragraph says, "The most obvious need today is for experimental data on rock deformation. We know very little of the processes which contribute to the permanent change of the shape of rocks. The data presently being gathered are of limited value inasmuch as deformation is being carried out under conditions of limited application and nature. The products of many of these tests doubtless bear little resemblance to natural rock fabric. At present, there is little to limit the imagination of the structural geologist in the interpretation of rock fabric." So his whole goal when he established the lab was to understand the processes that are occurring under natural rock deformation and try to, as he said, limit the imagination of the structural geologist. But I would say that he constrained the imagination, but he also extended the conditions under which we can imagine things about. So it was not simply limiting, it was extending in a very profound way. There is this wonderful confluence of walking into the lab and actually doing something, and that really appealed to me for a number of reasons. And then underlying all of it, before you go into the lab, you have to understand something about the physics of the processes that you want to look at. You can't just blindly wander in and do experiments. They have to be very targeted. And so the really nice thing of being able to look at Earth processes in the laboratory and do things, and then to have some sort of fundamental physical understanding of what's going on, essentially material science of rocks, I found very attractive. And then later on, after being at MIT, it was clear to me that the most important thing was none of those, but it's the people that you work with. So the people at MIT are just wonderful, and they're passionate and committed. There are a number of things that have, in the last 50 years now, which is about how long this lab has been here, that have occurred. So understanding of sort of fundamental processes like earthquake processes, the flow of fluids in the earth, understanding the physics and kinetics of creep processes that occur over long time scales, such as might be important in mountain building or plate tectonics. And then these applied programs that problems that I alluded to before. So understanding reservoir management, mitigating the effects of hydrofracture, understanding the way fluids flow in the earth and the way the permeability might change depending on what, and the interrelation of chemistry, physics, and deformation in the earth. So those are all things that we've made really significant advances. The critical and most important thing is that you're, in the experiments, that you're replicating or activating a process that you think is occurring in the earth. So the first thing is you have to have some intuition about the processes that you think are going on, and then you can design the best experiment for it. The sort of important things are trying to replicate as many of the conditions that occur in the subsurface. And so that involves pressure, temperature, fluids, because they're a really important part of rock deformation. Having samples that are representative and well-constrained is another important thing. And in order to get all those things, it's necessary for the machines to have ways to generate the confining pressure. And so in all the machines in the lab, there is some sort of confining medium that has to be produced. It has to be pumped to a high pressure. And then there need to be loads, additional loads, uniaxial loads applied to the material to make it deform. And if possible, and if temperature is important, then we need to heat things. So there need to be intensifiers, fluid pressure generators, measurements of the axial deformation, and then other sensors like PZT sensors or thermocouples. For creep experiments that occur over very long time periods, we trade temperature for time. So use the kinetic effect, the fact that things that occur very slowly are similar to those that occur at a higher temperature. So we'll trade off temperature for time. And so the experiments are sometimes done under temperatures that are much higher than the target materials we're trying to understand. And that's fine, but then you also have to worry about not activating other processes that are not going on. So you have to worry about the chemical stability of the material and make sure that you don't exceed that. And so the proper design of the experiment is really completely determined by the process that you want to do. And so it means that you have to sacrifice complexity in a lot of cases to focus on a single process. But the hope is that if you understand that single process and know enough about a mechanical constitutive model for it, that you can extrapolate it to the conditions that you're unable to achieve in the lab. For shallow depths, it's entirely possible to replicate the conditions, provided that you're interested in applications that occur over relatively short time periods. But if we're looking at natural processes that are deep, then we cannot replicate all the conditions. And the one that's the most serious is the time constraint. So some of the processes that occur in the Earth go for periods of 1,000 or more years. And so it's obviously impossible to replicate that in the lab. And there is, in addition, a huge span in spatial variation. So you know, when you're thinking of processes that are occurring in the building of mountain ranges, that's over the spaces of kilometers and much larger, and plate tectonics occurs over hundreds of kilometers. So there is scaling in time and in space. And then the final thing is that the materials themselves are very complex. So the chemical environment that is involved is very complex. But the approach and the way to get around that is to try to isolate different processes that you know are important, and to study those and study them in a way that you can extrapolate to the conditions, the natural conditions. But I would be remiss if I didn't say there are also a huge number of applied problems that can be dealt with directly. So reservoir management, acoustic properties, and so on can all be dealt with. And so that's the approach that we try to, and all the equipment that we use to do that it is specifically designed to isolate a few processes. And then the last thing I should say is that it's an important element of all these things to combine laboratory experiments, calculations, observations in the field to get an integrated sense of what's going on at these larger scales. So it's a stool, it has 3 legs, and it won't work without one of the legs. So that's a very important aspect. The greatest challenge is making sure that you have, in fact, limited the experiment and the things that you're measuring to exactly only be contributed by the process that you want to examine. So the higher temperature sort of experiments that are done with samples of this size mean that you can only measure 1 or maybe 2 different properties in the experiment. But in the larger, lower pressure kind of experiments, you can measure more than 1 property. So for example, you could measure permeability, resistivity, elastic modulus, and strength, and do that all in 1 experiment simultaneously. And then when you do that, you have this wonderful intuition about the interrelationship of all those physical processes. And that's a really important thing, because many times we're in the subsurface, we're limited to what we can see is down there. We have to know what's down there, say, from seismic measurements. So if you can measure the seismic properties while you're deforming something, then you can get an interrelation between the different properties that can be very useful. There's always an inverse relationship with the size of the sample and the pressure that we're going to. And when you see Mate Petch's lab upstairs, those are the highest pressure machines that are here at MIT. And the samples are much smaller. So for the low pressure kinds of experiments, the sort of sample size might be like this. So it's sort of up to 4 inches in our lab. And then the intermediate sizes that we often use in this machine over here are about 1.5 inches. And then for the highest pressure, highest temperature machine, the samples are quite a bit smaller, sort of 1 centimeter in diameter. So as pressure and temperature go up, the sample size goes down. And so that's an additional constraint on trying to extrapolate to high. The reason to do that, though, is that at the very highest temperature samples, we can trade temperature for time. And so you can extrapolate in temporal scale, but you sacrifice with a spatial scale.